OK, so multiple logical communication channels. What we just talked about with all these different message types here, plus like the 10 not drawn, can't all go on the same network at the same time. If you have one interconnection network or one logical network here, you could end up with cases where you have responses that get queued behind requests that will create more traffic. So in these protocols, we have multiple phases of communication. We send a message from point A to point B, and then from B to C, and then from C back to B, and then B back to A, or something like that. So if you try to overlay this onto an interconnection network, and you do head-of-line processing, so you process the message which is at the head of the queue first, it's very common to have something where you have a new response that sneaks in, which is dependent on some other transaction that's happening somewhere else in the system, and you're waiting for a new request that comes in that gets queued behind a response. Or excuse me, you have a new request that comes in which is in front of a response. And all of a sudden, you're going to have a deadlock. So one way people go about solving this is you look at all the different types of messages that you have, message types that you have, and you figure out which types can coexist on the network at the same time. So good example here is, I think, if you look at a relatively basic cache coherence protocol, there's maybe 12 different message types. You can try to shrink that down to maybe 3 or 4 different classes of traffic. That those classes of traffic, when intermixed, will never introduce a deadlock. If you want to be really safe, you would just have 12 separate networks, or 12 different networks, or 12 logical different networks. But that's expensive to build. So people try to come up with equivalence classes of different traffic and then only have that number of networks. But you're going to have to segregate these flows on different logical or physical channels to make sure you don't have deadlocks happening. Another thing I wanted to point out here is we just distributed our memory. So we need to start worrying about the memory ordering point. Or for a given memory address, where do you go, and what order did memory operations happen in? So just like in a bus-based protocol, you'll have some sort of arbiter which determines who wins a transaction or who wins the bus. In a directory-based system, typically the directory for a given address is the ultimate arbiter. So if 2 messages are coming in from 2 different cores who both want to get write access to a particular address, one of them is going to get to the directory first. And whoever gets to the directory first could win. Or that's typically will win. You could think of sometimes this could be unfair. So some of these systems, you try to have something which prevents the core, which is close to the directory, always winning access to that contended line, we'll say. So you might have some sort of back-off protocol playing into effect there. But this is what effectively guarantees our atomicity, is the directory it guarantees that a particular line can only be transitioning from one state to another state at a given time. So we have the directory as the ordering point. And whichever message gets to the home directory first, let's say, wins. Subsequent requests for that line are going to lose. So what do you do on a lose? Well, the directory is probably going to want to send a negative acknowledgement, or a NAC. It's going to say, or you can send a retry. It's the same thing here. It's going to say, I can't handle this right now. This line is currently being transitioned already. Someone else won the transitioning of this line. Go retry that transaction, the memory transaction, again in the future. Now, this gets pretty complicated back at the cache controller, because it's going to get a retry or a NAC back. It could potentially have a message coming in for that exact same cache line. It needs to give that directory's message priority, in this case, over the pipeline of the main processor. So it's going to have to order that after it, because the directory won. The directory is the ultimate ordering point for the memory location. Finally, you have to worry about forward progress guarantees. What I mean by this is it's pretty easy to build a memory system that you pull the data into your cache controller pulls it into your cache, but before you're able to do a load or store to that actual address, it gets bumped out of your cache. And all of a sudden, you have a cache line just sort of bouncing between two caches, and it's a live lock scenario. So when you're building these directory-based coherence systems, and this also happens with bus-based protocols, but it's usually a little bit less likely, you have to have some sort of forward progress guarantee. And the reason it's less likely is because in a directory-based system, the communication time is usually longer, so the window of vulnerability is longer. But your forward progress guarantee means that once you get into your cache, you need to at least do one memory operation to it to guarantee you've had one before you relinquish the memory back to the directory controller. So if you're doing a load, you actually bring it into your cache shared, do the actual one load, and then you're allowed to cough it up. So you don't respond back with the reply to, let's say, an invalidation request from the directory controller until you've done your one memory transaction. Or likewise, if you bring it in modified, you do that one store before you cough the data back up or release the data back to the memory controller. That's really important to make sure you have some forward progress in the system and don't end up with a live lock. OK, so we're going to get into the more future-looking stuff here. Oops. We've been talking about what's called a full map directory, where there's a bit per processor core. If you have 1,000 cores in the system, that's a very large bitmap. And it's pretty uncommon that 1,000 cores in the system will all be reading all of the data or all one particular cache line. So it might be wasteful. And your directory in a full map directory grows as order n. So that's not particularly good. So people have looked into different protocols here. I just wanted to touch on this. This is largely the area of sort of research and future directions of this. One idea here is to have a limited pointer-based directory. So instead of having a bitmask of the sharer list, so sorry, this is the sharer list. So instead of having a bitmask of the sharer list, you have base 2 encoded numbers up to some point. And this is why it's called a limited directory or a limited pointer directory, because you can't have all the nodes in the system on this list. There's not enough entries here. But you can name them because you have a base 2 encoding of the actual number. And if you get bigger than this entire list, so let's say you have 1, 2, 3, 4, 5 entries, and all of a sudden 6 sharers, 6 read-only copies of the list want to be taken, usually there's an overflow bit here, which says it's more than 6. And when it's more than 6, and it was shared, and all of a sudden it's a transition to modified, you're going to just send a broadcast message or send a invalidate to every single other cache in the system. But usually this can be a good trade-off, because it's pretty uncommon to have extremely widely shared lines. So it's an interesting trade-off there of storage space versus sending more messages in the system. Likewise, there's an interesting protocol here called limitless, where same idea, it's a limited directory, an overflow bit. But if it overflows, you start to keep the share list in software, in a structure in main memory. And this requires you to basically have very fast traps, such that when this happens, because you're servicing a cache line here, you interrupt the main processor, and the main processor provides the rest of the share list, for instance, if the share list gets overflowed. So there's a bunch of stuff in between and some future research that's still being done actively in this space. Beyond simple directory coherence, we have some pretty cool on-chip coherence. This is why this is actually being studied a lot right now, is people built these massively parallel directory-based machines in the past. They got some use. They're very good for some applications. But now we're starting to put more and more cores onto a given chip. So we start to see on-chip coherence and figuring out how to leverage the fast on-chip communication along with directories to make more interesting coherence protocols. There's something called COMA systems, or cache-only memory architectures, where instead of having data in main memory, you don't have main memory ever, and the directories move around. It's a little bit beyond scope of this course. Go read about the KSR1 if you want to learn about that. Kendall Square Research one. And then also just figuring out how to scale up the sharer list is active. Briefly, wanted to talk about the most up-to-date versions of these things. We have the SGI UV1000, which is a descendant of the Origin and the Origin 2000 machines from SGI. Lots of cores here. 2,560 cores that are all kept cache coherent. They use a directory-based coherence protocol here. It's very non-uniform, and it's all connected together by a multi-chassis 2D torus. So this is one chassis. There's actually up to 8 of these. Princeton has one of these in the HPC-RC center that I think is 4 chassis, which is sort of half the size of the maximum. An on-chip example here is the Tilera Tile 64 Pro. It has 64 cores, and each of the cores itself is a directory home. And it runs a directory-based protocol. And I was talking about dividing communication traffic into different flows. Well, there were 3 different memory networks here. So we had to come up with 3 different classes of traffic that themselves would not deadlock themselves, if you will. And also there's 4 memory controllers which just connect into our interconnect system. And because of this, the communication latency is different. A core here talking to the memory controller is very fast, versus a core there takes longer. But maybe this core is close to that memory controller. So non-uniformity here. OK, so this is the last slide of the term here. Beyond ELE 475, if you want to go on and do more, well, start reading some papers from different computer architecture conferences. The Proceedings of International Symposium on Computer Architecture, ISCA, is a good place to start. That's probably the top major architecture conference in the field. The International Symposium on Microarchitecture is the top microarchitecture conference. So if you're trying to look inside of a processor and some of the smaller microarchitectural details. ASP+, Architectural Support for Programming Languages and Operating Systems, has a lot of different crossover between software and hardware. It's a very good conference. And HPCA looks at, or used to look up at higher performing, big computers, high performance computer systems. But now a lot of normal computer architecture ends up in that conference also. And what else should you go do? Well, go do research, build some chips, build some test out these things on FPGAs, learn more about parallel computer architecture, and indeed, you can come back in the fall and take ELE 580A, which is going to be a graduate level primary sources paper reading course, more traditional graduate course, where you'll learn about all the different parallel computing systems. So we call it parallel computation because it's both parallel computer architecture and some programming models that hook together that and parallel programming together with the architectures, because they go very hand in hand. So let's stop here for today and stop here for the course.